Bismillahirrahmanirrahim. Hello, welcome to the deep learning course. This lecture is on the regularization. Salam and good afternoon to you. Azud. We are going to talk about qualitative learning in terms of regularization and the deep learning framework. Our main focus would be to point out some of the well-known methods of regularization, that is the methods that try to balance between the learning error in the training phase and the testing phase, and we then conclude the available approaches and there are some future directions. Let's start with a simple definition of regularization. Okay, let's continue with the regularization. Do you see my board correctly? Okay, I will use this for some notes, and this is the main presentation line. Then let's go. As I told, regularization is about training a model in terms of qualitative way. That is, when we train a model by some algorithm such as gradient descent or any other optimization algorithm, we are trying to optimize a cost function and find its minima, or if I try to say it more precisely, we are trying to find one of its minima, and it may be a global minima, it may be a local minima, it may be a good minima or bad minima. But the way we control the goodness of this minima, the goodness of this point, is up to the adopted algorithm, our approach of updating the weights, updating the parameters, and many other points. Regularization is a branch of learning that tries to control the model training such that the testing error is lowered as compared to the training error. That is, we try to lower the testing error, since, as you know, when we train a simple neural network in any type of neural network, assume a simple one, a very simple one with simply two inputs, ignoring biases, and okay, this is not W, this is x1, this is x2, and we have here some output variable y. We have some w1 and w2 here. We see that w1 and w2s are the parameters or weights, and we define an error function called e of w. We denote by this symbol the W vector. That means W is composed of at least two elements. Here it's composed of exactly two elements. In more complex networks, maybe it may have and would have several elements. Here we have just two elements of W. We ignore the bias term that would be here. For simplicity of our discussion, we ignore bias for now. And as you know, we use training data such as this one. Suppose that we have a training set, this capital T, and we feed this training data to the model to update its W's, W1 and W2. We get a best W by denoting it W star. We mean that this is the best W we got from the training procedure, training algorithm. This is a two-term or two-element vector, W1 star and W2 star, meaning that these values lead to the minimum of error function, or as we will say from now on, a cost function. A cost function or error function covers the learning procedure, and we are going to find its minimum point. However, this is the training data, and our trained model, let's call this model M. After training the model, M would have two parameters. This trained parameters, these trained weights would be M's parameters, and the M would be our trained model, and we will use it in production environment. That is, we will use it in predicting the output Y for unseen and unknown variables of X1 and X2. Suppose that this is of our universe of this course. Our training set comes from here, and this is the main world. Let's call it U, the first letter of universe or universal, and this is T. This is the subset of T is a subset of U. We used it for training, and so let's have here denote some other set here by T prime. Let's be unique in representing sets. This is another set T prime, also in T prime is also in U. It's also a subset of U, and these arbors come from the universe of this course, our set of all possible inputs. This U is our set of all possible inputs, and the error of our model, E of M on T, is training error. We call this training error, and error of M on T prime is the testing error. My mouse is not friendly with me today. This is the testing error, and this is one, this testing error, this is one that counts in productive environments, counts in production. It is important in production. Our customers would focus on this value, a model with very low training error but considerable testing error would not be fine for many of our customers. So we would try to lower this term as much as we can. Okay, we could try to lower this term as much as we can. Before going to the details of regularization, I will clarify at least 2 points of 2 sources of large testing errors. Let's pass over this network. We will get back to it a few moments later, but let's look at some classification problem in a 2-dimensional space. I will try to find this. This is a simple classification problem. Here is class 1 and this is class 2. Our task is to find a classifier that discriminates both classes from each other. That is something like this line, this line that separates the classes. It's a very good classifier. We will see it why it is good. We will see some moments later, a few moments later. This is also a classifier. Both of these classifiers, I will call these classifiers by their role, that is discrimination. I will call this classifier D1 and this classifier D2. Both of these classifiers are called zero error classifiers, since, as you see in the picture in the distribution of classes, they both separate the classes perfectly, but we prefer D1 to D2. Why we prefer D1 to D2? We say that D1 is better than D2. Why? Because as you see the picture, if a sample, for an instance, sample is the total, sample is a set of instances. Consider a sample residing here, just in the tangent point of the class and the discriminator function, that is D2, and let's start our measurement instrument, that the ruler or any other measurement instrument, the tool that we use to measure, to quantify the samples, to observe the samples, has some error, a ruler that estimates the correct properties of this sample. Let's call this one x1, this dimension x2, assuming that our ruler has some errors. We'll see that the error may push this instance towards the this axis, x2 axis, or out of it. That is, in one measurement experience with erroneous, with a ruler holding some intrinsic error in measurement, that is, let's zoom it somewhere, that is, in some measurement with some inaccurate ruler, we may have this instance here, or we may have instances, the instance here, and the classifier D2 is better than D1, since it will classify this, all these three measurements correctly. We have three measurements for an instance in the border of class, that is, this instance is in the border of class, and if the error has some, if the ruler has some errors on it, on the measuring capabilities, then these values may be measured for just a simple and a constant instance here in the border of the class. DDO will classify, let's denote these values by some name. I call this XA, this one XB, this one XA, this one XB, and this one X sub C. All these values are just XA, XB, and XC are just three versions of measurements made on the constant value of an instance. Okay? D1 will classify all of these instances. D1 will classify XR, XB, XC correctly. It would be assigned to C2, but D2 will make a mistake on XA at least. D2 of XA would be C1, and this is error. Why we get some error like this, why we get this error? It is because of the concept of margins. To point out the importance of margin, I would use another shape for just two other classes. Let's take those two classes and this classifier D. Roughly speaking, the margin of a classifier is its distance from the classes that are discriminated. We call this distances margin. You know that margin has very precise definitions in the statistical learning theory, and you know that, certainly you know that SVMs, support vector machines, are learning models that try to maximize this margin. We are not going to talk about SVMs for now, but I would name this here, this SVMs here, to just remind you on the margins and their importance and the max margin classifier of SVM to as a specialist in the learning with maximum margins, learning with max margins. Okay, that is the error. This error of Dido, is directly linked. The error of Dido is directly linked to its small margin, since the margin of Dido is very small. If you a little modification to a very little change on the value of measurements made by some erroneous, by some faulty device will push forward this values, this erroneous values in some wrong direction. Okay, my mouse won't help me today. I will go with some. As a faulty device, I use a faulty mouse today, and writing with a faulty mouse is terribly hard. Okay, that is, the error of this classifier is directly linked to its small margin. We will write it in some point here. Let's use this point here and denote that the first source of error, the first source of increased testing error is the small, let's start small margin of classifier. This is the first source of error. We'll try to build some robust classifiers and denote this small margin classifiers, as we will know this small margin classifier as non-robust models. Robustness is a term used to denote max margin or high margin, large margin classifiers, and conversely the small margin classifiers are those classifiers that are not robust. Okay, this is the first type of error that we see in many learning scenarios, that training error is very low, the training error is very low, but the testing error is high. The second source of error is the link to the dimensionality of the model. That is, let's draw another problem here, another classification problem here. Let's see if this has a this is the two classes. We will also talk about classification in this problem. Dear Nazud, you can ask questions any point in the lecture. I will hear you. Your microphone is open in Google Meet, and you can ask any question as you like. Okay. This is another classification problem. I will explain the second problem of high testing error in this scenario. Let's assume that this is the training set and the actual testing set. The actual testing set, or the universe of this course, is something like this. And let's pick another color for the second class. The solid lines, the solid blue lines, are the subsample training sets. That is, this is subsample training set, and the dotted lines is some testing set. Here our testing set also contains our training set. It's not a problem here. We don't care for now, but as you see the training set, a model may, a training algorithm may train some learning models with nonlinear shape. Considering the shape of class 2, C2, as you focus on, as you concentrate on C2, you see that it's parabola shaped. This is a parabola. As you see, since C2 is much like to parabola, a learning algorithm may be motivated to induce a parabola-shaped discriminator. We say this parabola, so let's say it P1. And it may induce many other parabolas as well, according to the initial point of the learning algorithm, initial setting of the parameter values. But we don't care about the robustness of the parabolas here. We just focus on the shape of this classifier. As you see, a parabola may perfectly discriminate the training and the training set, but as you see, the actual shapes of these classes, are ellipse. the shape of both of the classes is ellipse, and a parabola is not a perfect classifier. Here we can say that, as before, a simple linear algorithm may be a good choice, since we have some colliding area here. The classes are collided here. They are not discriminated clearly. Here is a area of error that both classes have some values mixed together here. I say this a colliding area. And any classifier, let it be a parabola, a line, a circle, an ellipse, or any other type of classifier, could not distinguish these instances here in this area correctly and perfectly. The large error of this parabola as compared to this, let's say it D1, the large error, let's pick the better color, the large error of D1 of T prime means the error of discriminator D1 on the T prime test data. T prime is our test data. The error of D1 on D prime on T prime is lower than this is error of D1 on T prime is lower than the error of P1, the parabola on T prime. Okay? The large error of parabola on T prime may be attributed simply to its complex structure. A linear classifier such as D1 is simply denoted by a linear first order equation between the variables and the parameters. That is, D1, D2 could be simply expressed by W1 x1 plus W2 x2 correlates to 0, or if you are going to use biases, you can put a bias term here and use another dummy feature of x0, meaning that we could have v, let's write it correctly. Okay, this is ignoring the model, the expression of D1, ignoring biases. But if you insist in using biases, you must use W0 x0 plus W1 x1 plus W2 x2. We say that x0 is 1 anywhere, and W0 is in this sense W0 is said a bias. Okay, this is with the expression of D1 with bias, and this one is its expression by ignoring bias. Okay, but for parabola, let's write the expression for P1. The parabola would have some expression like this one, W1 x1 as in the linear model plus W2 x2 plus 3 quadratic terms, 3 power 2 terms, quadratic terms, meaning W1 squared, no, W1 is not x squared, W1 is not x squared, W3, it's another parameters, times x1 squared plus W4, the force parameter, times x2 squared plus W5 x1 x2. Once again, we could have biases here, but I ignore this term since it does not make a difference in our explanation of the models, and it could be treated as a simple constant feature in our discussion. Okay, here D1, let's pick this version of D1. D1 has two simple parameters. P1 has several other parameters, W1, W2, as in the linear model, but W3, W4, W5 are additional parameters, and this way we say that P1 is more complex than D1. Okay, the complexity, that is, the complexity of a model is its set of parameters. It is denoted by the set of its parameters. That is, a model with large number of parameters is more complex than a model with fewer parameters. Okay? The larger of P1 here is linked to this number of parameters. That is, if a model has more parameters, it may have, or we expect that it will have a large testing error as opposed to the simple models such as here we see between the parabola model and a linear model. Okay? Let's recall and remind some points from statistical pattern recognition, and we will see why this happens in learning scenarios, why large number of parameters leads to why large number of parameters leads to higher testing error. I will not go deep in this the philosophy of this phenomenon, but I will recall some points from statistical pattern recognition. There we saw that in pattern recognition with statistical models, we saw that if we have a model with n parameters, n is the number of model parameters. For example, for a simple linear model we had here, n is 2. Here we had 2 parameters, or with bias we had 3 parameters. For parabola models we have much more parameters, at least 2 times of the linear model. And if generally for a model with m parameters and m classes, that is the number of parameters, n is the number of parameters, m is the number of classes. For example, for binary classification with a linear model, for binary classification or a dichotomy with a linear classifier, for example, for this model here, we have 2 classes, we have 2 parameters, and m is 2 classes. A rule of thumb, that is, why we say rule of thumbs, by saying that it's a rule of thumb, we insist that it is a rule, or it is a bound that is created by experience or by inspection of many experts in this area. As a rule of thumb, I say it's a rule of thumb, then you will not go for a proof on it. We will need a training set with at least 3n, this is the smallest number of instances, to 10 times n instances from each class. That is, if we have a binary classification problem with two parameters, then we should prepare NS2, we prepare at least 6 instances from each classes. Since we have two classes, 6 plus 6, resulting 12 instances are needed to train a classifier that will have the training error by using this amount of training set. We could make hopes that our classifier's training error will be close to its testing error. That is, the classifier is D, E of D for training error would be close to E of D for testing set or testing instances. However, this is the minimum number of samples to collect, to prepare. The recipe says that please provide more instances close to this bound. This is the lower bound and this is the upper bound. The books advise you to prepare more samples close to 10 parameters, 10 times and 10 times of the parameters. Let's jump to deep learning architectures, deep neural networks. Okay? Now, the first 6 is for first class. I assume that we have a binary classification problem. If you have a multi-class classification, then you need 6 instances from each of the classes. That is for 4-class problem. For 5-class problem, 5 times 6, 4 times 6 samples from each of the classes. Okay? Okay, let's continue. Let's jump directly to deep neural networks. For deep neural networks with many parameters, for example, for deep neural networks for tens of millions of parameters, we would need large amounts of training data. We would need, for example, for a deep learning architecture, we'll easily have somewhat 10 to 6, that is a million parameters. This is very realistic in deep learning scenarios. Then we would need tens of millions of instances for training the model sufficiently. Let's get a point here for a detailed discussion on the number of training instances required for training a model perfectly. You can consult the topic of probably approximately correct learning. It's a branch of, it's a topic in the PAC learning. It's a topic of classic pattern recognition, will derive some nice bounds on the number of instances required to train a model perfectly. Okay, we will pass over it. However, the issue remains here. For a set of 10 million parameters, we need at least 30 million instances to train the model with the satisfactory levels of errors on both training and testing sets. Okay? This is the second source of errors, that is the large number of parameters. Here's the large number of parameters. And most of the time, these large number of parameters are not of the same importance. That is, many of these parameters are there by mistake or by an idea that is meant to be used in some other area for some other aspect of the problem, but the evaluations, the measurements are there. For instance, data logger or a person who prepares the data for use, for example, has some columns here in the data set that these columns are not required for your current learning task, but it is required for some other learning task, and using these columns here just makes your task more complex, more difficult to accomplish. Okay, this is the second source of error, in the second source of large testing error in our learning scenarios. I will denote it as small in large number of parameters and I will say, since we are in the discussion on the basics of this regularization theory, let's shed some light on another simple source of error. It is not an disjoint set source of error. It is not another or independent source of error, but it is closely related to those of the previous sources. I will say it as the third source. Needs no more discussion. It is the lack of sufficient training data. That is, lack of sufficient training data. That is, your setting of model is perfect. Your number of you have selected the best set of parameters. You have selected the best learning model. You have selected developed the best the network architecture, but you don't have enough data to train the model sufficiently. This is closely related with the two previous sources. More closely with the second one, that is governs the relation between the parameters and the number of data points. To keep on with the time of the class, I will focus on the first source in this session, and we will continue the second source in the future lectures. Okay? Regularization, by definition, regularization is any modification we make to a learning algorithm that is intended to reduce its generalization, or generalization has the same concept as testing error, the error or production error, the error our model makes on its unseen instances, and we do not care about the training error. What does it mean? Simply, it means that if your training error is something like, for example, 5%, by this TR I denote the training error. Suppose that it is 5% that our model has made erroneous decisions on 5% of our data set in training, our training data set, and our testing error, I denote it by TS, is 15%. I'm going to discuss this concept. We would definitely like another model with training error. Let's be some high value here. For example, we will prefer a model with 25% of a quarter, 25% of error. That is, our model has made error on a quarter of samples roughly, but a TS of its testing error is something like 10%. We would love this model. Why? Since it will work in the production scenarios, it will, our customers, our users of our models will see and will experience this amount of error in the field, in the production stage. However, for model, for example, let's say this one M1 and this model M2, this model is M1 will have 15% error, meaning that its error in the viewpoint of our customers, users of our model, will be much larger than the error of M2. That is why we would love to reduce generalization error or testing error, and we would ignore the amount of the training error that we make. Okay? The training error, the value is the value we see here in our side, in our laboratory, in our experience, in our experiments. But the testing error is the error that our customers, our users, our money makers, those who will pay for our model will see. Okay? That is, regularization is any modification we make to a learning algorithm that is intended to reduce its generalization error but not its training error. For this lecture, I will try to make a classifier somewhat robust. That is, I will try to mitigate the small margin of classification. I will try to increase margin of classification with just a bunch of simple ideas. Please note that these ideas are very simple but very helpful in designing successful learning procedures. Okay? Let's clear out the third item of error. Any comments, Najud? Okay. Let's assume once again that we have two classes like this. We have two classes like this, and this is our classifier. Just sticked into the classifier. This is C1, this is C2. It's just sticked, just is very close to the class 2, C2. To make this classifier more robust and to push it away from C2, that is, to push away this way, to push away it this way, I will provide two simple ideas. The first one is from your AI course in the bachelor's in undergrad. That is, make several versions of this classifier. As you remember, when you try to build a linear classifier by some algorithm such as gradient descent, the first step is to initialize the learning parameters randomly. The first step of a gradient descent algorithm is something like this: init w, the w to small random values, and do the updates. I don't write other steps, since the other steps is simply using the derivatives to update the w's iteratively. However, I will focus on this simple step of making initial w's. That is, suppose that for one trial we start from a w that is 0.1, both are 0.1. In another trial we may start from a w with 0.2, 0.1, and many other versions of this initial value. As you know, gradient descent algorithm is a iterative algorithm, and it keeps going on, keeps updating the parameters until it gets into a minimum error, or in many scenarios a zero error point at which it stops updating. That is, let's say that a first assumption may be something like this one, and further updates of this may make this assumption more accurate like this. That is our first assumption. For example, this is our first assumptions. Gradient descent updates this value, updates this line to be this one. This is our second step, the line in second step, and as we measure the error here, we see that the error is 0, and we stop the training procedure. Then once we stop here, the first, let's get back to this one, our perfect line, let's say the perfect line is something like this. We keep this line and repeat the learning procedure as the first one. That is, we assume that we have this problem in hand, we did not solve it, we try to solve it again, we start from another point, we may have this line, and this line may lead to, by gradient descent, this line may lead to do some classifier like this, and we generate several versions of this classifier starting from random initial points. I say this classifiers all with minimum or zero error classifiers. These three DK. K is selected by experience, or an algorithm may select it by the time used to train the algorithm. That is, if you determine the total amount of running time, that is, you train the algorithm for a couple of hours and stop the algorithm, and then write down the trained classifiers and select best of them. The first step makes many classifiers. The second step just selects best of them. We can use many criteria for selecting the best classifier. For example, we can subsample this training set and generate some validation set and exclude the validation set from the training set and evaluate the classifiers, the induced classifiers on this validation set to find the best one. This is a simple idea. I will call it multiple trials. Please note that it is not synonymous to ensemble methods. Multiple trials. The multiple trials approach, the multiple trials approach, finds a set of initial classifiers but selects a single classifier out of them. It results in just a single classifier and drops others. Okay? This way we would have a single classifier naturally equivalent to its structure is the same as the others, but it is one of them. It is not a mix of them, it is not an average of them, it is not an ensemble of them. However, we will talk about ensemble methods that use all of these classifiers to make a more complex group-based, to make a more complex group-based decisions, group-based learnings. We will review approaches such as bagging, boosting, gentle boost, and similar approaches. Okay, this is our first effort. It's multiple trials. It's very simple idea. Anyone in the field of experience in the field of experimental studies, anyone in the field of experimental studies in computer science, in AI, or any other physics, chemistry, and any other field of study will know this approach as a simple approach that leads to some powerful method, powerful model, powerful approach out of many available approaches. This is our first effort, our first idea. The second idea is as simple as the first one, but it seems more powerful in many practical scenarios. Suppose that we have once again the same learning procedure, the same learning problem. We have these two samples, we have these two simple classification problems. The field circles are from class 2 and the MP circles are from class 1. A learning algorithm may learn this model that has very little margin, or I will say for this case a margin with width of 0 width. It is a 0 width margin, a width of 0. However, I use a simple idea. Let's just this simple idea. It is, for example, it is our first instance. It has two. Let's x1, this is x2, it has two features. Here I say that x1 will be 2 by, let's 1, 2, 3, 4, and here, okay, 1, 2, and 3. Approximately x1 would be 2 and 3. Its features are 2 and 3. I will make 3 copies of it just by a random selection of multipliers. Suppose that I will make for this sample, I will make another x1, another copy of x1. I will make its copy 2. I will call it copy 2. Very rare notation. However, x1 plus r times x1. What is r? R is just simply a random value. R is simply random value, for example, meaning in the range from 0 to 0.1, or let's use the other side of the axis. It may be from minus 0.1 to 0.1. It is just a random value. For example, I will pick just this one, 0.01. Then this version of x would be, let's add it by its scaled version. Its scaled version will be its original version multiplied by this scaling factor, that is r is a scaling factor, and we will have 2.0.2 and 3.0.3, meaning that our new instance will be somewhat here. Okay, our new instance will be somewhat here. I drew it somewhat more far from the original version, but it must be some point here. It's for clarity. I drew it in some more distance. Okay. No, it's up to you. For simplicity, we will use very small values. That is, this is a large value. 0.1 is very large value, but mostly we will use 0.01. This is a very good one. Okay, and what's the question? No. You know, it's not fixed. It's the range. The bounds are also up to you. These bounds are also up to you. You may select any other bounds. However, let's go ahead. This one, the new sample, is not from the original original training set, but it gets, since it's very close to x1, This is x1, and it is very close to x1, and the continuity assumption of learning theory says that close objects, the objects near to each other, this is the continuity assumption. As you remember from our earlier lectures, the continuity assumptions says that objects near to each other share the labels. That is, closed objects have the same labels, same class labels. Okay? Okay. That is, this version of x1 will also belong to class C1. I will call this class C1 and this one C2. And if we continue this procedure and make more samples, let's do it hypothetically. Hypothetically, let's do this. I will make more samples out of x1 here just by the random selection and generation of samples. This will be class 2. And what we would have the new problem will have more training data. The new problem has more data, and it will learn some lines like this. Okay? It will learn some lines like this one, and the new one, the new discriminator, the new model, D2 is the new model, has margin much larger than the initial one. Thanks to this fabricated instances, our new model has much larger margin. Okay? This is the notion of data or data augmentation. What does it mean? It simply means that if you have a few training instances, if you want to have more training samples, but you are training instances, but you are not going to sample from the field of the objects, you can generate hypothetical samples. You can generate fabricated samples out of the available instances by just scaling the existing samples and moving them around the available ones. Okay? Is it clear? Okay. Well, okay. This is the notion of data augmentation. It's very simple, but it has many applications in generating robust learning models, robust neural networks, robust statistical models, since it makes more classification. Let's draw another shape for this one. That is, this is the original training data, and we make this training data. For simplicity and directedness, I will just plot the instances near the boundary of the classes to be more focused on the discrimination and the margin. I will just plot the values near the boundary, and the new fabricated instances forces our learning algorithm to devise, to learn a more robust model. This is a simple approach for data augmentation, or making more data, making larger data sets instead of out of available data sets. However, It is not the most efficient one. It is not the most used one. We will see in the autoencoders section. The topic. It is a topic of. It's a very important topic of our courses, and we will have a few lectures on it. We will see there that autoencoders and the rating models are also another alternative for making these new instances, for generating new instances and making augmented training sets to induce robust models. Okay, it's enough for today, and we will continue our discussion on the regularization in the future lectures. Any comments? Okay, we'll meet in the, hopefully we will have, let's take a look at our calendar. Do we have any lecture this week, or we'll have the lecture next week? I see that. Okay, we will have another lecture in the next Monday. Hopefully we will continue this direction on the regularization in more ways, in more advanced approaches for regularization. We will talk about L1 and L2 regularization for shortening the number of parameters, for eliminating the set of unused parameters from the models. We will need some background from linear algebra. I will highly encourage you to consult the first few chapters of the book. The chapters, let's see, please study chapters 1 and 2 once again, since we will have a very quick overview of the regularization techniques by matrix factorization and some other related concepts. Okay, for now, goodbye.